Okay, so let's go ahead and get rolling. I'm running a little bit behind right now, so I was planning on using my Surface so I could write things out for you, but my Surface crapped out. So I'm not going to be able to do that, so I can't write, unfortunately, on a blank sheet here because I'm using a PC here, or actually I'm using a Mac, but so I just don't have the ability to write or annotate. But that's okay. I think we can still make it through this. So if you're just joining us, hopefully you are seeing my screen and you are seeing this poll over here, exam 2 Q&A. So we've already got people asking. Quite a bit of people want to go over this already. So I'm going to go ahead and jump in right there. I have over here the practice exam, knowing that there's, of course, going to be questions on that. Don't limit yourself to questions off the practice exam. I can take any question. And don't also limit yourself to just asking responses or questions on this poll. You can go ahead and interrupt me. You can, unmute yourself and interrupt me. I can't really access the chat on Microsoft Teams when I'm sharing my screen, so probably not the best place for the chat. I guess I could pull this up, so I can do that. Okay, so I'll try and look at the chat every once in a while, or the conversations, just in case something's going on. So okay, I have started the recording. So let's go ahead and get rolling on this. I do think it's important to go ahead and say that the exam, of course, is going to be tomorrow. The format of the exam is identical to that of exam 1. Meaning that there's going to be 2 matching questions, and there's going to be the multiple true-false questions, and then the short answer question. So nothing different there, nothing new there. You do have more time on this exam. I recognize that in our last exam, people really actually were pushing towards the end of that time period. The average time for a student to get done with the exam was 52 minutes. Of course, the maximum time was 60 minutes. So that means that a lot of people were needing more time, I think. So I went ahead and gave you that time on this exam. The other thing that I did, let me go ahead and look at the practice exam here. There actually will be more of this on this exam, but it says some potentially useful information where I'll put equations and that kind of thing. I put that scattered throughout the exam because some individuals had told me, well, it was hard to scroll all the way to the top of the page, look at that, and then have to scroll all the way back down to my question. So I went ahead and put this, I think there's like 5 of them placed periodically throughout the exam that will come after, I think, every like 5th question or something like that. So, or every 10th question or something. I can't remember how often it is, but that way it'll prevent you from having to go all the way to the top, all the way to the bottom. So, okay. All right, so let's go ahead and look at our first question here. And our first question says this: can we go over the answer? I can't see this. The answer to the first short answer on the practice exam. Absolutely. Let's go ahead and do that. So let's go ahead and pull the practice exam up here. So we're all on the same page. Okay. Let me go ahead and get this all on the same page there. There we go. Okay. And I'll zoom in here just a little bit. There we go. So everyone can see it. Okay, so this is our question, and the question is essentially asking you to predict the affinities of a hemoglobin molecule for oxygen, a hemoglobin molecule for carbon monoxide, and then it states that there's going to be these distal histidine mutations, right? So one of them is a distal histidine that's been mutated to a glycine, and the other one is a distal histidine that's been mutated to a tryptophan. Okay, and then it asks you to draw these curves. So I think that the really important aspect of answering this question is to think about first, what does the distal histidine do in the normal subunits, right? So the question asks you, we'll just plot out a curve for the normal subunits, okay? And normally the distal histidine is going to provide a hydrogen bond to the oxygen that is bound to the heme group. Okay, of course, oxygen forms a covalent bond to the iron atom, and then that oxygen atom, I'm sorry, not atom, but that oxygen molecule will then can form a hydrogen bond to the distal histidine. Okay, so if you think about the distal histidine, let me go ahead and come here and give you a picture of this. Here we go. So the distal histidine would be, sorry, I overshot it. This guy right here, okay? Let me go ahead and get rid of some of these things for us because there's a lot there, okay? But this is the distal histidine right here, and it's forming this hydrogen bond with oxygen. This is the heme group of hemoglobin or myoglobin. Okay, but this is oxygen, this is that hydrogen bond, okay? So that's what the distal histidine is doing. The proximal histidine is down here. It plays a different role, a different function, okay? Now, when you think about then carbon monoxide, let me go ahead and just state this. If we have carbon monoxide here, remember carbon monoxide, coming back to this, will stand straight up in the oxygen binding pocket. Okay, so this is what oxygen looks like. It's bent, whereas the carbon monoxide will stand straight up. Okay, and because it stands straight up, that distal histidine is essentially sitting right here. You can see my cursor versus right here for oxygen, and it runs into the carbon monoxide. So that's the function of the distal histidine. It's to stabilize interactions with oxygen by forming a hydrogen bond, or it clashes with the carbon monoxide. Okay, and that's really what the distal histidine's function is. Okay, and that will then set some regular affinity. Okay, the question really though here is to help you understand, well, what would the affinities of these mutations be relative to the normal subunits? Okay. Now, some of you might be sitting there saying, okay, real quickly though, and I can't draw on this, but some of you are thinking, okay, is the curve for carbon monoxide, is it sigmoidal or is it hyperbolic? If it's hemoglobin, it's more than likely sigmoidal. Okay, we didn't talk too much about carbon monoxide binding to hemoglobin and the cooperative nature of hemoglobin for carbon monoxide. But in all likelihood, it would be sigmoidal and it would be cooperative. Okay. Now, I wouldn't hold you to that in the exam simply because we didn't talk about it in class. But if you are wondering, I think that it would be sigmoidal behavior. Okay. And the affinity of course, hemoglobin for carbon monoxide is higher than it is for oxygen. But I'm not asking you to do it on the same curve. Okay. Now, in this, it says those subunits with a distal histidine that have been mutated to glycine now. Okay. What is that going to do to the affinity of hemoglobin for oxygen? And what is that going to do for the affinity of carbon monoxide? Well, glycine, if you remember, is the smallest side chain that is found in the 20 naturally occurring amino acids found in proteins. So you take away, if you go back to the distal histidine here, right here, you take away all of this imidazole ring right here. In fact, you even take away this carbon right here and you replace that carbon with a hydrogen, which means that when we think about oxygen binding, it no longer will have a hydrogen bond to glycine because glycine is not polar. So you're losing a hydrogen bond. And therefore, you would expect that the affinity of the mutant for oxygen would go down because it can't form the hydrogen bond to the distal histidine. Okay, it's now what would be called the distal glycine, if you will. Okay, because there's just no hydrogen bonding potential for glycine. Okay, now carbon monoxide, you would expect in this case, you're removing all this structure and you're placing all the way up here a hydrogen. You remove essentially the clash that would happen with carbon monoxide as it tries to enter this pocket. And because you remove that clash, then the affinity of that heme and that hemoglobin for carbon monoxide would actually go up. And we'd expect it to have a smaller KD because the glycine is just not going to clash with carbon monoxide. Okay, so that's what I'd expect here. So you would want to show a curve that has a smaller affinity for oxygen and a greater affinity for carbon monoxide in the glycine mutation. Okay, and then finally, when we look at this with subunits with a distal histidine that has been mutated to tryptophan, in that case, we have a much larger side chain than you have even with histidine. Okay, so tryptophan is a 6-membered ring that then has a 5-membered ring fused to it. So come back to this. We would have a 6-membered ring here and then a 5-membered ring here. And that would make it really crowded binding pocket. And so that would, I would imagine, decrease the affinity of hemoglobin for both oxygen and for carbon monoxide, because it's going to crowd oxygen binding and it's going to really crowd carbon monoxide binding, right? The histidine already crowds it, and then you add a 6-membered ring in here and it's going to really crowd it. So it's a real bulky side chain. Okay, so coming back to then our exam, you would want to probably show a curve that has, again, a decreased affinity for oxygen and a decreased affinity for carbon monoxide. Okay. Now, some of you might be sitting there saying, okay, so for oxygen, both mutations decrease the affinity. Which one does it more? You would really need to do an experiment to know that. I would think that tryptophan would. That was what my intuition would tell me. But I wouldn't hold you to which one is going to cause a greater decrease in affinity. I would want to see it relative to just the normal subunits. Okay. Some of you might be thinking, well, are all the curves supposed to be sigmoidal, or are they supposed to be hyperbolic? That I wouldn't hold you to that either. I would think that, again, the hemoglobin molecule will remain cooperative, even though you're changing the dyslicity. Okay. All right. So hopefully that handles that question and helps those of you that were interested in that question. Okay. If not, let me know, interrupt me. I'll check the chat here to make sure that we don't have anything. Okay, so it doesn't look like I have anything going on in the chat. Okay, so so let me come back then, minimize this, and come back here and go on to our next question. Now remember, this poll is still active, so keep responding to it. Okay, there we go. So keep asking questions here. We'll try and get through as many as we possibly can. Okay, now this one says, why does a lack of BPG in question 52, number 52, display decreased cooperative binding? All right, let's do this. Question number 52, I'm assuming we were talking about this one. All right, so it says, if 2,3-bisphosphoglycerate, or what we have called BPG, were not present in the blood, the oxygen binding behavior of hemoglobin would, number 52, display decreased cooperative binding. All right, so good question. This is a true statement. And so let me go ahead and come back here again, because I can't draw on my screen, which is a big bummer. I wanted to be able to do that, but my surface just didn't cooperate. Okay, and let me come here. And we'll look at BPG. Okay, so here's BPG. This is this is the molecule BPG. This is hemoglobin, as it says here, in the T state. And this red thing that I've drawn here is the regulatory site, and it's also where BPG binds. Okay, and BPG prevents the beta subunits from collapsing on one another. So this is the R state, and the beta subunits will collapse on one another. So if you look at this pink line here, right there, and you look at this pink line right here, right, and then you look at these pink lines here and here, both of them in both representations are outlining the position of the beta subunits relative to each other. And you notice there's this gap between them in the T state, and there's not a gap between them in the R state. All right, and BPG, if it binds right in between the beta subunits, which is essentially where it is, that red dot is where it is. Okay, this is a more detailed analysis of it. But that's where it binds. It prevents that collapsing from occurring. Okay, so it turns out that if you remove BPG, okay, you actually have a molecule, even though the T state can be stabilized by those ionic bonds that we've talked about, that do stabilize the T state, BPG helps stabilize the T state as well, okay? And it can shift that T-R state equilibrium towards the T state. So if you were to completely remove BPG from the solution, then you would have nothing helping those ionic bonds stabilize the T state, and you would have a much greater shift towards the R state. So much so that you would lose quite a bit of the T state, and you would have what would be considered less cooperative. Okay, it doesn't say it's not that its cooperativity is gone, but it would have decreased cooperativity because you would start, even at very, very low oxygen concentrations, you would start with more R. And therefore, there would be more molecules that couldn't have a communication of oxygen binding at one site through a conformational change to those other sites. Okay, so that's what would be going on, right? And that's why cooperative binding would decrease. Okay, if you hear things in the background, my kids, I'm at home right now, so my kids are doing their thing. They've got school still at home, so if you hear things in the background, then that's what's going on. I told them to be quiet, but they're kids. So anyway, okay, so hopefully that helps people understand that. The main thing with cooperativity, remember, is that communication is occurring from what's happening at one site to those other sites in the protein, and the best way to do that, really the only way to do that at a molecular level, is through conformational changes. And so if you have thousands of hemoglobin molecules, the majority of which are adopting our state, that there's not that much communication that can occur. Okay, and that's what would happen in the case of missing BPG. Okay, now next, come over here. So trying to get this. Okay, so the next one, how does substrate concentration influence Km, Vmax, and VO relationships? Okay, so it influences it hyperbolically. Sorry,
I think someone had a question in the chat.
Oh, great, thank you. Let me look. I didn't check. Okay, so can you make your screen a little bigger when going over the exam questions and notes? I will, yes, I'll try and do that. What did he say happens to molecules because of decreased cooperativity? Okay, I didn't really say what would happen to molecules because of decreased cooperativity. I more said that if you have missing BPG, you would have decreased cooperativity because there would be more molecules that have already undergone the conformational change that allows communication to occur from one site to another. Okay, so that's what I was trying to say. And when you do that, then you decrease cooperativity, right? So let's take myoglobin as the extreme example. Myoglobin has no conformational change, right? So there's not just decreased cooperativity, there's no cooperativity, okay? So then if you have hemoglobin and you have, let's say, 1,000 molecules, 900 of them are already in the R state, well, that's going to have decreased cooperativity compared to a situation where 500 of them are in the R state and 500 are in the T state, right? Right. So hopefully that helps out. And yes, I will try and make that bigger. I'll figure out how to do that, okay? Okay, now, coming back to our question, and thank you for interrupting me and telling me there's questions in the chat. I need that interruption. Okay, all right. So this one, how does substrate concentration influence Km, Vmax, and VO relationships? So it's a little bit hard to do here. Let's come back to here, okay, and let's draw this. Let's draw this out. Okay, I hate to point you to this, but I think the best way to point to this is quantitatively and also graphically, okay, and try and understand this. When we look at Km, Km is independent in many ways of substrate concentration. Okay, it is a constant, and the constant Km is best defined by saying it's the substrate concentration at 50% the maximum velocity, okay? But it doesn't change based off of changing substrate concentration, which is the way this is worded seems that, like, how does substrate concentration influence Km? Well, it doesn't influence it, meaning that we can't change Km by changing substrate concentration. Km is a substrate concentration. It's a specific substrate concentration where we're at 50% or maximum velocity. Okay, so best to look at this on a curve. We have a Vmax up here. We have then, let's say, half Vmax here, 50% point here. I draw this dotted line over here until I reach my curve, right? And then I drop that down here on my x-axis. I have the substrate concentration. That specific substrate concentration is the Km. Okay. Of course, we've talked about the Km as being a measure of the specificity of the enzyme for its substrate. And that's a very good way to think about that. Larger Kms mean it takes more substrate to reach 50% Vmax. Smaller Kms mean it takes less substrate to reach 50% Vmax. Okay, and of course, if we have smaller substrate concentrations required to reach 50% Vmax, that means that the enzyme is more capable of binding substrate, even when concentration of substrate in the surrounding environment is not very high. Okay, and that would suggest that its affinity for substrate or its specificity for a substrate is high. Okay, now how does substrate concentration influence Vmax? Same thing. It doesn't. Vmax is not dependent upon substrate concentration. In fact, if you look up here, Vmax is equal to Kcat NE total, meaning that if we change Kcat, Vmax will change. If we change the concentration of the enzyme, Vmax will change. Notice that we can't change, even if we change substrate concentration, you won't be changing Vmax. Now, having said that, there's a relationship between Vmax and substrate concentration, and that is this. When we are at what would be considered unlimiting substrate concentrations, or what we have called saturating conditions, we are at a point in our enzyme curve where we are at the Vmax. Okay, and that means this, that all of the enzyme is in the bound form. And the only thing that is causing the reaction to be slow or fast is something that happens after binding, right? So let me go here. Well, I guess I could have used any of these. Let's just use this one down here, okay? And hopefully people can see that. Let me see here. Try and, this is not as nice. Oh, that made it worse. Oh, no. Okay, there we go. So I think that's probably the best I'm going to be able to do with this, okay? But if you think about this, okay, this is, I mean, this is using our marble example, but we have, hopefully you have enough information in your mind right now to understand that we could map this over any one of the enzymes that we've talked about and say that these steps here would be those specific catalytic mechanisms, right? This first step, the formation of ES, is the binding event, okay? And then we have steps after that, okay? If we start our reaction here at ES, and in saturating conditions, you always start here at ES, okay? You're starting at a ton of ES, where really there's no free enzyme because you're at saturating conditions. In that case, then, what slows the enzyme down is one of these three steps, here, here, or here, okay? And those can't get faster, okay, because we've reached the physical limitations of the enzyme, and therefore at saturating substrate concentrations, you're at what we would call essentially the maximal velocity. Can't get faster, and this is where I think the marble analogy is, I think, really relevant. If I grab a marble, right, and I have to run a 100-meter dash to get it to the next box, that my overstep is definitely my rate limiting step. It's what slows everything down. And if I get myself at my age, right, in tip top, the best condition I can absolutely be in, I will obtain some maximum rate at which I can move a marble from point A to point B, okay, if it's a 100-meter dash. And no matter how much training I would do after that, I couldn't really get much faster because there's physical limitations that my body has. And that's what we're saying about the enzyme. You start here, one of these is going to have some physical limitation that's going to cause you to be at maximum velocity. at saturating conditions. Okay. Okay. And then it goes on to say this. The question says the relationship between. Oops. No, we're looking at this one. How does substrate concentration influence Km, Vmax, and then VO relationships? Now, VO does. Substrate concentration does have an effect on VO. Let's come back to this mathematically. Okay, so this is VO, right? It's on the other side of the equation from all this other stuff. So VO is right here. And when we look at substrate concentration here, it affects it in a way that causes this hyperbolic behavior. So that as substrate concentration goes up when we're at low substrate, it'll cause almost a linear change in the rate, or in VO. Whereas as you start to get to higher and higher substrate concentrations, it's the amount of effect that the substrate concentration is having on the rate starts to be minimized until finally you get out to saturating conditions where it has really no effect on it at all. Okay, so hopefully that answers that question for those of you who are wondering about it. Okay. Okay, let me check and see. Moving on, I'm going to move on. Okay, so there doesn't look like they're okay. What's the difference between Km and Kd? Oh, okay, great. So while we're on this subject, Km and Kd, the Km is applied to enzymes. Kd is applied to ligand binding proteins. They both mean very, very similar things. So the Km means the substrate concentration at 50% of the Vmax, a measure of an enzyme specificity for a substrate. The Kd means the ligand concentration at 50% saturation. Okay, so hemoglobin doesn't bind oxygen and convert it to something else, so it's not an enzyme, right? But it's Kd is the ligand concentration where 50% of the hemoglobin molecules have oxygen bound and 50% don't. Okay, so very, very similar concepts. In fact, Km and Kd can be the exact same thing when looking at some enzymes. Okay, so in some cases, some enzymes, Km is the enzymes Kd as well. Okay, so it's a fine line difference between the two. Okay, so good question. All right, now let me go ahead and go on here. We looked at this one. So we did that one. Now let's do this. Can you go over 36 through 40 on the practice exam or enzyme graphs? Yes, let's do that. Okay, so here's what I'm going to do. Okay, because people are saying this is too small. I'm going to do this. I'm going to stop sharing, and then I'm going to reshare, and I'm going to reshare only the practice exam. Okay, and then I'm going to make this bigger and zoom in a little bit. Hopefully that helps out. Okay. Okay, so let's go. It's 36 through 40. That's the one that we're looking at here. Okay, let me get this all on one page so we can look at this fairly easily. Okay, so it says this. In the following graphs, 4 different curves are illustrated, each of which represents an enzyme that obeys Michaelis-Menten kinetics. Given these graphs, which of the following statements are or is true? Okay, so let's just real quickly say something here, okay? And let's just say, well, actually, let's go ahead and look at the questions because I think it's going to give us conditions, okay, for this, okay? So let's look at 36. If all these enzymes have the same Vmax, they must also all have the same kcat, okay? So the same Vmax, meaning this, if we were to draw some line out here, they would all eventually reach asymptotically that Vmax range, okay? And so they're all going to get out there. So this says they'd all have the same kcat. Well, not necessarily, because we don't know the concentration of the enzyme, okay? Because Vmax is equal to kcat times the concentration of the enzyme. Now, if it said this, if all the enzymes have the same Vmax and E total, they would all have the same kcat, and that would be a true statement, because they'll. Just a second. It's okay. Just leave it out there. Yeah. So anyway, sorry about that. I just got interrupted. But so anyway, so if they all have the same enzyme total and they all have the same Vmax, then they all would have to have the same kcat. Okay, so let me go all to the top of the exam. Oh, it's not on this exam. Awesome. Okay. Well, I don't have, without leaving this, I don't have anything. Okay, so let's just leave it at that. Okay, Vmax equals kcat times E total. If you have the same concentration E total, same Vmax, and then have the same kcat. We don't know anything about E total for this question, so we can't say it's true. Okay, I have to say it's false. All right, now number 37. If all these enzymes have the same kcat, enzyme D is the most efficient when substrate concentration is much greater than Km. Okay, so if all of them have the same kcat, right, enzyme D is the most efficient when we have what's called saturating conditions. Okay, you don't even really need the curve for this. Let me think about what it's saying here. Yeah, you don't need the curve here. What this is saying is substrate concentrations, and this is maybe not the greatest question as I'm looking at it, but it's saying that you're at saturating conditions, okay? And if you're at saturating conditions, then the best way to measure the affinity, the efficiency of the enzyme is indeed the kcat, okay? Kcat, if you remember, is the rate constant of the rate limiting step of the reaction, okay? And so we're at saturating conditions, but there's nothing on this graph that really can tell you if D's kcat is greater than or less than A, B, or C's, okay? It doesn't, the question 37 doesn't say assume Vmax is the same for all of them, okay? And we don't know where D is going to level off. We don't know if D has some Vmax that's here, or has it here, or has it up here, okay? So we don't know enough information. We don't have enough information about kcat. Now, if it were to give us different Vmaxes for these, and it were to say that, you know, the Vmax for D is right here, and the Vmax for A is right here, then we could say that, oh, because the Vmax is lower for D than it is for A, then its kcat is smaller, and we would say well, we would still say it's false, okay, because it would be the less efficient than A. Okay, we just don't have enough information though in the question. Okay, number 38. If all these enzymes have the same kcat, okay. Oh, I'm sorry. It says they have the same kcat. I totally lost my bearings on number 37. They have the same kcat. If they have the same kcat, then they're all equally efficient at saturating conditions. Sorry, I should give myself a big red check minus. So I give myself a red check minus because they have the same kcat. Okay, because they have the same kcat. If they're at saturating conditions, then we can say that they're all equally efficient. Okay, kcat is the way to measure efficiency at saturating conditions. If they're the same, then they're the same efficiency. Now it says this. Maybe I got ahead of myself. It says if all the enzymes have the same kcat, okay, enzyme D is the most efficient at substrate concentrations less than Km. Okay, well this is at non-saturating conditions. All right, and the best way to measure the efficiency of an enzyme at non-saturating conditions is the kcat divided by the Km, or what we call the kcat-Km ratio. Okay, they have the same kcat, right? But they have definitely different Kms. Okay, so you can see that they would each of them have A, B, C, and D have different Kms. It would look like D has the largest Km and A has the smallest Km, right? And because A has the smallest Km, then the kcat ratio, kcat-Km ratio of A is going to be quite a bit larger than the kcat-Km ratio of enzyme D. Okay, and so because of that, then we would actually say that A is the most efficient relative to B, C, and D. Okay, because its Km is better or smaller. Okay, so this would be false because it says that D is the most efficient. Number 39. If all these enzymes have the same kcat, enzyme A is the most efficient when substrate concentration is less than Km. So this is again at non-saturating conditions, and that's essentially what I just said. A's Km is the smallest. Its kcat is the same as B, C, and D, and therefore, because of that, then we can say that that its kcat-Km ratio is the largest, and therefore this is the most efficient enzyme. And then finally, the specificity of A for S is greater than D for S. Okay, That's correct. Again, you can measure Km on this. Okay, and when we measure Km on this, D has a large Km, A has a small Km. Okay, small Kms mean more specificity. It takes less substrate to reach 50% or 50% saturation points, or 50% Vmax. Okay, okay. So stumbled on number 37. Sorry about that. Okay, got interrupted with something and I got distracted. But anyway, right now let's see if there's any chat questions on that one before we go on here. Conversation. Okay, doesn't look like it. So, all right, so I'm gonna go ahead and move on. I'm gonna go back to sharing my whole screen. And go here, okay? The relationship between Kcat, concentration of S, and Km. We have really been kind of answering most of that. Let me just kind of maybe summarize some of these things that we've been saying. Kcat is the rate limiting constant, or I'm sorry, it's the rate constant of the rate limiting step of the reaction. When substrate concentrations are really high at saturating conditions, we want to use that to measure the efficiency of an enzyme. Okay, that would only be at saturating conditions, and that would mean that concentration of S is really high. Km is the specificity of the enzyme for its substrate. Okay, and I think I've already really answered the relationship between for Km and the relationship to concentration of S. So this is really similar to me than question as this one up here. Okay, so let me go ahead and move on from there. If there's additional questions about this, go ahead and put it in the chat. Okay, if not, then we'll move on to our next one. Okay, but let's look at this 51 through 55 of the practice exam, BPG and its significance. All right, so I'm gonna go ahead and make this a little bit larger. I'm going to keep sharing this screen though. That way I don't have to switch back and forth. Okay, so that hopefully will be good for everyone. Okay, so we've already kind of done a little bit of this one. We did 52, but we might as well do 51, 53, and 51, 53, 54, 55. Okay, so we're taking BPG out. The action binding behavior of hemoglobin will be what? Okay, so it turns out I had actually an email about this question this morning too. So this one's kind of, I think, tripping people up. Maybe it's because we didn't talk about it too much in our lectures. Okay, or if we did, we're real clear about it. BPG. It turns out that if you were to remove BPG from a solution of hemoglobin, it would look not identical to, but very similar to, in terms of its oxygen binding behavior, to that of myoglobin. Okay, so there would still be some T state because there would still be ionic bonds between the subunits, okay, and within the subunits. But those ionic bonds are necessary for the molecule to form the T state, but they are in some cases not sufficient. And by that I mean you have to have BPG also sitting between two beta subunits, stabilizing the T state. Okay, you remove that BPG, and you lose the majority of the T state, and the majority of the molecule just collapses to the R state, even when oxygen is not there. Okay, and so then 51 resembles that of myoglobin, and that would be true for the most part. Okay, I don't know if I have. Let me see if I have a slide of this. Thought that I did. No, I don't. Okay, I don't have a curve where BPG's gone. So I have a curve where we're increasing or decreasing BPG. Okay, so this is BPG at 5 millimolar, 8 millimolar, and you can see a shift to the right. If you keep removing BPG, this would shift this way. Okay, and it would become less and less sigmoidal because you are losing more and more of the T state, and more of the molecules are in the R state. Okay. All All right, so that's the answer to that. 53, require more oxygen to reach half the maximal binding capacity. Absolutely not. As you might hopefully understand at this point in time, when you start removing R state, right, and this is the way you have to think in biochemistry about these things, we have thousands of hemoglobin molecules, right? Some of them are adopting the T state, some of them are adopting the R state. We remove BPG, it turns out the majority of them start to adopt the R state, okay? Well, in that case, then you don't have a lot of the molecules that are in a low affinity form that would cause it to require more oxygen to reach half maximal binding capacity, which is essentially the KD, okay? What would happen is your KD would go down and it would take less oxygen to reach half maximal binding, okay? Remember, what this is saying, half maximal binding capacity, that's 50% saturation. And the KD is again, the ligand concentration required to reach that 50% saturation point. Okay, so removing BPG, a negative heterotropic modulator, would actually cause it to require less oxygen, not more. Okay? Be less sigmoidal, we already talked about it. It would decrease the cooperative binding. We've really talked about the fact that it would be less sigmoidal. The reason to be less sigmoidal is because, again, if you think about 1,000 hemoglobin molecules, there would be, you know, when there's no BPG, there would be, I don't know what the percentage would be, but there would be this really high percentage of them that are already in the R state. Okay, and therefore you wouldn't have nearly as much cooperativity as you would if you had normal BPG concentrations. Okay. And then 55, indicate that the T state is stabilized relative to the R state. No, this would indicate that the R state would be actually favored. Okay, BPG stabilizes the T state. Right. So if you remove this, the oxygen binding behavior. Let's read the question. If BPG were not present in the blood, the oxygen binding behavior of hemoglobin would indicate that the R state is stabilized relative to the T state would be the true statement. Okay, so you'd lose a lot of the T state. Okay, now just so you know, this would never happen. Okay, you couldn't do this. This would kill you for a number of reasons. So you could do this experimentally in terms of not in the blood, but you could do it in in a reaction vessel and see those things. But not going to happen in an actual human organism. Okay. All right. Let me check my chat here and see if we got any chat going on. All right. So does an increase in BPG also increase P50? If so, how and why? Yes, it would. P50, so just to make sure that everyone's all on the same page, P50 and KD are the same thing. Okay, they're mathematically identical. They're just slightly different ways that we talk about these things. All right, but yes, it would increase P50 or KD, meaning that as you increase, in fact, let me come here. As you increase BPG, so I have BPG concentration here at 5 millimolar, that's this curve. And you have BPG concentration at 8 millimolar, that's this curve, okay? So we have gone from, in this binding experiment, to this binding experiment, the only difference is that we've increased BPG, and you can see what's happened here. Our 50% point, okay, where our 50% saturation point has shifted to the right, meaning that it takes more oxygen when BPG concentrations are 8 millimolar to reach 50% binding, okay? Again, the reason for that is because BPG sits, let's do this, sits right here in the T state, and it prevents these two beta subunits from coming together, forming the R state. Okay, so it just stabilizes the TR equilibrium towards the T state. Okay. Okay, excellent. All right, let's leave BPG for now. I think we've talked quite a bit about that. Let's go to this next one. We've still got some time. Okay, so it's 1:48, so we'll give it another 12 minutes or so. Okay, so can a catalyst change the free energy of a product or reactant? No, absolutely not. What does this mean in terms of the catalyst's ability to change the equilibrium constant and change it? I think that this is a study guide question, and change the, I think it goes on to say the delta G of the reaction. All right, so catalysts cannot and will not change the free energy of a product, and they cannot or will not change the free energy of a reactant. Okay, they change activation energies. That's about it. Okay, but what this really means is that an enzyme or a catalyst cannot make an inorganic reaction exergonic and they can't make an exergonic reaction endergonic. Okay, they can only make a reaction reach its equilibrium point faster, and that's it. Okay, so this goes on to say this, right? Well, does it change the equilibrium constant? No, it doesn't. Okay, it can't change equilibrium constants or the equilibrium point. It just allows them to get there faster. Okay, so if we go back to here, this is lecture 6. We drew all these free energy diagrams, man. We drew a lot of them. And so that one's okay. Yeah, let's use, I guess any of these would be fine. Okay, so what this is essentially saying, let's go ahead and use this one. What this is essentially saying is that where this starts and where this is, where it ends, those are going to stay the same whether the enzyme is present or not. Okay, in fact, if you were to compare this to this product is the same here, this substrate is the same here, okay, and the enzyme's not changing those. It changes lots of stuff in between reactant and product or substrate and product, but it doesn't change anything in the starting point and the ending point. Okay, these portions here and here will be what we call those are the rate independent variables. Okay, and the delta G of the reaction, which is essentially the difference between our final state and our initial state, that is a rate independent or a path independent variable. Okay, and therefore the rate doesn't change those. Okay, and that's true then of equilibrium constant as well, because the equilibrium constant is a direct reflection of the delta G of the reaction. Okay, let's check my chat here. If I can find it. Where is it? There you go. What effect does a catalyst have on equilibrium? Does it change equilibrium? Okay, so we just dealt with that. Okay, good. So it doesn't. Will the fetal hemoglobin be included on the exam? Oh, good question. I'm glad. Yes, it will be. Yep. So that would be LN08F. And if you listen to that, I said to that class that semester, this won't be on the exam because honestly, I think they'd already taken their exam. So we are going to put it on this exam. So yes, you'll be held accountable for that. Okay. Next, let's move down here. Keep working our way. How does KD relate to affinity of a protein for its ligand? It is the measure of affinity of a protein for its ligand. So small KDs mean large affinity, and large KDs mean small affinities. Okay. Now, again, just to reiterate, KD is the concentration of ligand required to reach 50% of the saturation point. And so if it takes small amounts of ligand to reach 50% of the saturation point, which would mean the KD is small, that would mean that the protein has a high affinity, okay? Because it doesn't take very much ligand to reach 50% of saturation point. But that would be relative to something that had a large KD, which took a large concentration of ligand to reach 50% saturation. So, okay. Could you go over the short answers for the practice exam? So I already did one. Let's go ahead and look at the second one, though, okay? And if you missed the first one, I'll go ahead and go back to that one, okay? All right, so practice exam, let's find it. Okay. Here's the second one. Okay. I don't know if you can hear my kid in the background. He's like playing with his puppy. So I think he's getting bit and he's screaming. So anyway, so, all right. So lunchtime or something like that. But anyway, so given this information, oh, we gotta have the information that we were given. Where is it? Oh, there it is. All right, so the structure of a newly discovered protein has the following structural properties. The primary structure is 408 residues. It has one chain. It's got 5 disulfide bonds. I'm going to highlight that. Secondary structure, 10 alpha helices, 4-stranded antiparallel beta sheets, or 2 4-stranded antiparallel beta sheets. A well-formed hydrophobic core. That's important. Okay. 8 buried salt bridges, also important, and then a number of exterior electrostatic interactions. Okay, so we got all that. Oh, let's do delta H first. So predict the sign of delta H and give a brief explanation as to why you chose that sign. Okay, is delta H going to be positive or is it going to be negative? Now remember, And again, this is where I really wish I could draw something out. But remember, delta H is equal to H bonds broken minus H bonds formed. Okay. And so when we think about a protein folding event, we have to think about, well, what bonds are being broken and what bonds are being formed in the process. And when we think about the protein in its unfolded state, this is in a biologically relevant situation, just as it says, biologically relevant conditions. The unfolded state of the protein would form interactions with water, and it would form interactions with the sodium in the chloride and the other anions and cations in the solution. Okay, meaning that the unfolded state of the protein would have hydrogen bonds and it would have ionic bonds, okay, to the surrounding solution. Okay, now all of those bonds, we have to understand, need to be broken because the protein needs to start to interact with itself to form its final structure. And so during the folding process, then it starts to lose those bonds to water, and it starts to lose those bonds to sodium and chloride, and it starts to adopt bonds to itself. Okay, and of course we know, hopefully you know by now, that a protein will form hydrogen bonds to itself, and it will form ionic bonds with itself, right? And so we have bonds broken, hydrogen bonds, and ionic bonds. We have bonds formed, hydrogen bonds, and ionic bonds. Okay, and so if you leave it at just that, we would say, well, it could be that delta H is debatable. Okay, however, in this question, let's come back up here, it says specifically that there are 5 disulfide bonds that are formed. Okay, now some of you might be sitting there saying, well, those are listed as primary structure, and primary structure is the unfolded state. No, the primary structure is not the unfolded state. The primary structure is simply a description of the sequence of amino acids, or the covalent bonds holding the structure together. Okay, disulfide bonds form in the tertiary structure. Okay, don't think about the primary structure as the unfolded state. We don't think about it as that. Okay, but we do list disulfide bonds because they're covalent bonds in the primary structure. Okay, covalent bonds that hold amino acids together in a protein. Disulfide bonds are part of that. Okay, all right. So those form. Now understand that in our bonds broken value, there are no hydrogen bonds. I'm sorry, there are no disulfide bonds between the surrounding solution and our protein in the unfolded state. So when it folds and it forms disulfide bonds, those disulfide bonds only contribute to bonds formed, and there is no offsetting bonds broken, the covalent bonds and the bonds broken value. Okay, so that makes bonds formed much larger. So we already have a solid argument to say that this is negative, because the disulfide bonds only form are only forming, and there's no covalent bonds that are being broken as we proceed from the unfolded to folded. Okay. The second thing to think about here is this. Okay, it says buried salt bridges. Buried salt bridges are salt bridges that are buried in the hydrophobic core, and because they're buried in the hydrophobic core, they are ionic bonds or salt bridges that are surrounded by a nonpolar environment. Those are stronger ionic bonds than any of the ionic bonds that are forming in the unfolded state. Because in the unfolded state, we have ionic bonds to sodium or chloride, but they're all surrounded by water. And ionic bonds, when they're surrounded by water, are weaker than ionic bonds that are surrounded by a nonpolar environment. Okay, so we have then ionic bonds, sure, they're breaking, right? But they're breaking, they're weaker ionic bonds that are breaking compared to some of the ionic bonds that are forming. Okay, and therefore, again, our bonds formed value is going to be larger than our bond broke value, again, making for a negative delta H. Okay, so good reasons to think that delta H is negative. Okay, delta S, positive. Okay, and the reason it's positive is because there is a hydrophobic core that forms, meaning this, that the hydrophobic side chains of the protein in the unfolded state interact unfavorably with water. Okay, meaning that the water entropy is low in the unfolded state. As the protein folds, the water entropy increases drastically because those non-polar side chains get tucked into the interior of the protein. And so the entropy of the solvent goes up. Now, the entropy of the protein itself, the conformation of the protein, goes way down. Okay, but because there's more water than there is protein, the delta S is going to be positive, okay, because of the hydrophobic effect taking place, okay? But I would want you to describe what that means, right? Don't just say, oh, it's positive because of the hydrophobic effect. Describe what that means, okay? Solvent entropy is increasing, essentially. Delta G is negative, always. And Vincent demonstrated this. So there's an experiment that demonstrated that this is true, run by Christian and Vincent, okay? We can also say, well, if this is negative and this is positive, then we know that this has to be a negative delta G, okay? Okay? So now my kids are arguing with each other. so let's do this. It's 2 o'clock. So what is the main difference between cooperativity and allostery? Let me answer that question because I think that I can quickly go over that. Okay. And then we'll leave it there. I'm sorry I couldn't get to everything, but that's the nature of these things. Okay. So what is the main difference between cooperativity and allostery? The main difference is the type of modulator. So cooperativity is going to be homotropic modulation. Allostery is heterotropic modulation. Okay, so when we say that something's cooperative, we could say that, okay, molecule X binds to the protein, induces a conformational change, and changes the affinity of the protein for molecule X. So it's molecule X binding, changing the affinity for molecule X. Okay, homotropic modulation is X of X binding of X. Okay, so that's cooperativity. Allostery is when we have molecule X binding to the protein, inducing a conformational change that affects the affinity of the protein for molecule Y. All right, so there's heterotropic, that are X and Y are different. Okay, hemoglobin is both allosteric and cooperative because it has BPG that can bind to it and affect its affinity for oxygen. So BPG is molecule X in this case, oxygen is Y. Or it could have oxygen binding that then affects its affinity for oxygen. Okay, and that would be molecule X to molecule X. Okay, so it's both cooperative and allosteric. All right. All right, so let me go ahead and end there just to respect your time. And also I have another meeting after this, so I have to get going. I hope that this helped you out. If you have like lingering questions that just didn't get answered here, go ahead and send me an email and I will try and get through those things or and a reasonable amount of time. So, okay. All right. So there's a video of going over both free responses in Echo 360 if you came in late. Oh, okay, great. That was right. So, okay. Yeah. All right. So take care, everyone. I hope that you rock this next exam. So I'm going to go ahead and stop the recording, and I'm going to go ahead and hang up on you all. Okay. So and you're welcome. And lots of people are saying thank you. So you're welcome. It's my pleasure to help you guys out. Okay. So good luck. All right. Take care.